Okay, so picking up 5-1 part notes here, we left off on part B of example 1. So part B again, to find the average force, anytime they ask us to find the average force, we're just taking advantage of the force times time equals change in momentum. So all I'm doing is taking advantage of that equation, which represents the average force equals the change in momentum. So I don't have to use a graphical representation. Once I know the change in momentum is 9 and the duration is 6 milliseconds, or 6 times 10 to the negative 3rd seconds, I just find the average force using that. And then part C, obviously I have a beautiful graph down here representing it, but they just ask us to graph the change in momentum, or to graph the momentum before and after the collision. Well, before the collision, the ball is moving backwards, or what I defined as the negative direction, so it's here at -3 kilograms times meters per second. And then after the collision, I know it's up here at 6, and then I know during the collision it is a curve, it is not a straight line, it is a curve, since my function was not a straight line function up there. But other than that, not a terribly difficult, hopefully, example to look at. So example 1 finished out. Again, if you have any questions over that, just let me know. Example 2, I believe. Yep. So example 2, very similar to the one we just worked. They ask us how high does the ball bounce. They give us a graph, and really all this one entails is basically 3 different stages. And again, I know I've got the work laid out here. I'll go through this in just a minute. But let's think about the problem. So you've got a rubber ball, it's dropped from height. They ask us to find out how high it bounces. They do give us this graph. Well, since they give us the force up here, the maximum force, and the duration of time, we can find the area underneath that graph, right, since it's just a triangle. So if I find the area underneath the graph, which is represented down here, that area just represents my change in momentum. So I know how much the ball's momentum changed when it hits the floor. So if I want to figure out how high it's going to go, I'm going to take advantage of that by finding out what was its momentum right before it hit the floor, and then using the change in momentum to figure out what's its momentum right after it hits the floor. So basically there's kind of 3 stages to this problem. There's the stage of when the ball was dropped until it hits the ground. So we know that from the time it's dropped until it hits the ground, it's in free fall. So I'm just going to use kinematics to help me find the velocity, right? So that's what I did here. I just used kinematics, I set it up, I found the velocity right before the ball hits the ground. So that -6.26 meters per second is representing its velocity right before it hits the ground. Notice I did go ahead and define that as negative since it is going downward right before it hits the ground. So that helps me then find my initial momentum. My initial momentum would just be my mass, which they gave me was, what was it, 100 grams, right? Yep. So they give me the mass, and then I've got that velocity. So then I simply have to find my final velocity by using the change in momentum. I know the change in momentum is the area underneath the curve. I know that the mass of the ball is 100 grams, so 0.100 kilograms. I'm looking for my final velocity, and I know my initial velocity was -6.26. So I set up my change in momentum. Once again, the most important thing is because the direction changed, this needs to be either a negative or positive, and this one's going to end up being the opposite of that sign. Right, so in this case, because I made downward negative, that's why it ended up being positive. But anyway, 5.74, so that tells me how fast the ball is leaving the ground. And then since they ask how high does it go, I just do one final stage of kinematics here, where I then use the final velocity that it leaves the ground with as the initial velocity for the flight back up. Right, so the ball bounces off the ground, it goes back up. Right when it leaves the ground, it has that initial velocity of 5.74. because that's its final velocity after the collision. So I have basically, again, those 3 stages. Hopefully nothing though too tricky. I just have to find my initial velocity before I hit the ground, my change in momentum, and then my height based upon the final velocity resulting from that change in momentum. Obviously, if you need to pause this and go through any of the work, feel free to. But like I said, I'm going to keep moving to try and get this part down here. So anyway, the final kind of new thing, if you will, in this section that I'll show you is one more relationship between momentum being conserved for an isolated system. So this time we're actually going to use Newton's third law. So once again, I made a mistake on the initial document, but we fixed that. It is now using Newton's third law, which is the law that says for every force there's an equal and opposite force, right? Forces come in pairs. So what this is representing is maybe the force from object 1 on object 2, and this would be the opposite force that goes from object 2 back on object 1. So I think hopefully you guys agree that if object 1 exerts a force on object 2, object 2 would exert an equal but opposite, and I included the negative to make it opposite force on object 1, right? So using that relationship and then solving to get both of them on the same side, I know that those two forces, because they're equal and opposite, the sum of those two forces would have to add up to be 0, right? If I had a 10 Newton force and a negative 10 Newton force, obviously the sum of those two would end up being 0. So that's nothing new. Well, again, force is just mass times acceleration, and we know acceleration is dv over dt. So mass times acceleration, but I really know that each of those accelerations is just dv dt. So then if I isolate the dt's, if I multiply dt on both sides, obviously that would get that off the bottom on the left hand side, and it would end up being a 0 times dt over here. I'm going to go ahead and kind of leave that dt hanging around, but it is multiplied by 0, so keep that in mind. But anyway, the reason that I do that is then when I integrate both sides, and so this is really the integration of this entire side, but when I integrate both sides with respect to the appropriate variable, so on the left hand side I'm integrating with respect to v, on the right hand side I'm integrating with respect to dt. Well, on the left hand side I ended up getting mass 1 times velocity plus mass 2 times its velocity. And on the right hand side I have 0, so I don't end up with any t's, right? 0 times t would just be 0, but I do get that constant term. And so hopefully what this kind of then shows us is the momentum, mass 1 times velocity plus mass 2 times velocity, is always equal to a constant measurement. So again, this is just taking advantage of Newton's third law, which says forces always come in pairs, to show that momentum has to be conserved if there's no outside force acting, right? If the only forces acting are the forces between two objects, then because they're always equal and opposite, momentum always has to be conserved. If we just use a little bit of calculus, we can show that. So again, not the type of thing that you would necessarily have to reproduce. It is something though that I want to make sure you guys kind of think about a little bit, spend some time in thought. Make sure if you do have any questions, you let me know. But hopefully that kind of makes sense where that comes from. And it's obviously something we took advantage of last year as well. So then last two examples are basic conservation of momentum examples. Example 3 here is a nice way of kind of intertwining some graphs with momentum as well. So we've got a 250-gram air track glider. It's pushed across a level track and it collides with a 500-gram glider that is initially at rest. The figure below shows a position versus time of the 250-gram glider, and then best line fits have been shown. What is the speed of the 500-gram glider after the collision? The key here is this is a position versus time graph, and so if we think about it, what does the slope of the position versus time graph represent? Well, the slope represents the velocity, right? So this is the graph for the 250-gram glider, but basically what they're telling us is they're giving us a graphical representation to find the velocity. I really don't care about the starting point nor the ending point over here, right? I don't care about those quantities. What this is telling me is my initial velocity for the 251 is 0.75 meters per second, and my final velocity for the 250-gram glider is negative 0.21 meters per second. So that gives me some very important pieces of information. Once I realize that, again, it is a collision. There's no outside forces acting, so I know that momentum is conserved. I know the initial momentum needs to equal the final momentum, which means we can break it up as mass 1 times its initial velocity plus mass 2 times its velocity equals mass 1 times its final plus mass 2 times its final velocity. Hopefully that looks very familiar to what we did last year. And at this point it's just a numbers game, right? It's just a matter of plugging everything in. So we know the initial mass of each of them. We know the initial velocity of both object 1 and object 2 because they did tell us the 500-gram glider was at rest. And then I know my final velocity for object 1. So I really know 3 of the 4 velocities, which then gives me a route to find the fourth velocity. Once again, the most important thing we do realize here, and the graph did it for us, but we do need to make sure we realize if it changes directions that it is a negative velocity. Again, the graph kind of represented that for us, and then it's just a matter of solving this out. So the final velocity for the 500-gram cart is 0.48 meters per second. Again, hopefully a pretty basic problem compared with what we did last year. Maybe a good review of momentum, but as long as there's no outside force, we know momentum is conserved, which gives us a route to then set this up. So then last problem, actually one I did not work in class, so I will at least set this up here help you guys get started, but it's probably one you can work through on your own as well. So feel free to, if you'd like to pause the video, or if you would like to simply try this on your own. If you're confident you can do it, feel free to do so. You don't have to waste any more time watching this. But anyway, Professor Portner sees a stationary cart 8 meters in front of him. Despite his best attempts to do otherwise, he channels his inner child and decides to run at the cart as fast as he can, jump on, and roll down the level street. He has mass they give us, the cart has mass that they give us, and he gives us, or they give us, his acceleration as well. What is the speed of the cart just after he jumps on? The key to this question, the reason I did throw this question back in, again, just to review, if he jumps onto the cart, so initially you've got Portner, he sees the cart over there. By the way, this is never to be mentioned that Portner is in an example. He might not like that, so we just won't mention it. But anyway, he jumps onto the cart, and then because he jumps onto the cart, we are assuming that he and the cart moved together, and the cart also somehow got bigger after he jumped on it, and they're now rolling together, which, because we're conserving momentum, means my momentum equation would look something more or less like this. His mass times his velocity plus the mass of the cart times its velocity equals their two masses together, right? But they're now moving at a common final velocity. And that's the key to this problem. As soon as you realize they have a common final velocity, this problem hopefully is not too bad. We do have to do a little bit of kinematics here because they don't give us his initial velocity. We do know that the cart is initially at rest, so this is just 0. So we have to do a little bit of kinematics to find his velocity. So they give us the distance. We will assume, of course, that he starts at rest. So his initial velocity is 0, his acceleration is 1, and the distance is 8. So obviously, if I'm looking for the final velocity, I'm using those measurements to help me out. So then going from there, I know, again, I'm looking for his final velocity, his initial velocity, and then they give me the acceleration of the displacement. So I'm using this kinematics relationship. I'm looking for his final. His initial velocity is 0. His acceleration is 1, and then the distance that he travels is 8. So I obviously set this up fairly nicely here because this is just 16, and I think we can do the square root of 16 without a calculator. So his final velocity as he jumps onto the cart would be 4 meters per second. So then that represents his initial velocity before the collision. So we've got a 75 kilogram mass times 4 meters per second, plus, again, 0 there for the cart. It equals the total mass together, so 100, as we take the cart and the Portner and add them together, and then find the final velocity from that. So 75 times 4, I believe that ends up being 300, divided by 100, we get their final velocity to be 3 meters per second together. Notice it did end up being positive, which tells us it goes in the same direction that he was originally going. But again, the big concept I do want you to be comfortable with here is this is a collision where they stick together. The next section will actually redefine those for you, but this is what we refer to as a perfectly inelastic collision. Anytime two objects stick together, we refer to it as a perfectly inelastic collision, but hopefully nothing too tricky there. Anyway, that finishes out the first section of notes, and really section 2 will also be primarily review. So what I will probably do for that section is I will give you the example page, and then I will allow you guys to look at my key. But I doubt that you have any major questions, so I don't know that I will make a video unless you guys feel that you need me to, in which case just let me know and I will do so. But anyway, hopefully the calculus in this section wasn't too bad. If you guys do have any questions, like I said, just come find me, let me know, and I will see what I can do to help you out with that.